British and South Korean scientists are teaming up to reach the depths of one of the world's biggest glaciers.
At the edge of Antarctica, a glacier the size of Florida is breaking itself apart. Not in silence, but with earthquakes.
Cracks are continuing to grow at an alarming rate on the icy continent of Antarctica.
Deep, slow, and unmistakable. Scientists once believed the collapse would come gradually. Then, beneath the ice, a robotic probe found something no one expected: staircases of melt and vertical wounds. The collapse isn't beginning, it may already be accelerating. The silent fracture. For decades, Thwaites Glacier appeared to be holding steady. Satellite images showed a massive, unyielding slab of ice stretching from the heart of West Antarctica into the Amundsen Sea. To the naked eye, it looked immovable, cold, ancient, and unmoved by time. But beneath the surface, forces were gathering that no one could see. The glacier's outward stillness masked a deep instability growing at its foundation. Long before the world heard the phrase Doomsday Glacier, subtle warning signs were echoing through the ice. Seismic stations, originally placed to monitor tectonic activity, began recording strange signals, low-frequency pulses buried in the background noise. At first, scientists dismissed them. Some thought they were data glitches or the sounds of natural ice settling. But these tremors weren't noise. They were the first whispers of a fracture so vast and so quiet, it nearly went unnoticed. By the time researchers realized what they were hearing, it had already been happening for years. Something was shifting beneath Thwaites, something relentless and mechanical. And as the signals multiplied, so did the urgency to understand what, exactly, was cracking open at the bottom of the world. Earthquakes in the ice. It was Dr. Sarah Chen at the University of Washington who finally traced the source of the anomaly. She wasn't looking for glacial quakes. She was combing through years of archived seismic data, chasing patterns in what most believed to be meaningless static. But buried in that data, beneath the hum of Antarctica's wind and shifting snow, she found a pulse, low, rhythmic, and consistent. It came from the front of Thwaites Glacier. The frequency was unlike anything seen in tectonic earthquakes. These signals registered between 0.01 and 0.1 hertz, far too slow for traditional earthquake monitoring systems to detect. Yet, when Dr. Chen cross-referenced data from seismic stations hundreds of miles apart, the pattern held. The signals aligned across multiple locations and timelines. They weren't glitches, they were earthquakes, but they weren't coming from faults in the Earth's crust. They were coming from the ice itself. Further investigation revealed more than 360 distinct seismic events, all clustered at the ocean-facing edge of Thwaites. Unlike ordinary iceberg calving, which occurs sporadically, these quakes repeated. They were not one-time ruptures, but signs of continuous structural failure. Each seismic pulse was a message from the glacier, a record of fracture and stress, echoing through bedrock. When Dr. Chen's team coordinated with researchers from the British Antarctic Survey and Germany's Alfred Wegener Institute, the findings became undeniable. The glacier was not stable, it was in motion, not forward across land, but downward through integrity. It was breaking apart under its own weight and friction, broadcasting its decline to anyone willing to listen. The silence had been broken. Thwaites was speaking through earthquakes. Collisions that shatter the seafloor. Most people picture glaciers calving gently, massive slabs of ice drifting silently into the sea. But what's happening at Thwaites is not gentle, it's violent. Icebergs the size of skyscrapers are tearing free, not drifting away, but rotating in place like wreckage caught in a whirlpool. Then, with devastating momentum, they slam back into the glacier wall that birthed them. This isn't a single impact. It's a repeating cycle of destruction. Once an iceberg detaches, ocean currents and wind begin to pivot it. As it spins, the sheer mass, often tens of millions of tons, builds torque. When it crashes back into the glacier face, the force is equivalent to multiple megatons of explosive energy. That shock doesn't just split more ice, it travels downward through hundreds of meters of ice into the bedrock itself. Seismic stations as far as 500 miles away register these impacts clearly. The collisions aren't flukes. They're part of a system feeding on itself. Each impact causes more fractures. More fractures mean more calving. The new icebergs rotate, collide, and the cycle repeats. Researchers call this self-perpetuating fragmentation, a runaway loop where Thwaites uses its own mass as a weapon against its structural stability. Worse, these impacts often ground the icebergs on the shallow Antarctic seafloor, dragging across ridges and slamming into underwater terrain. Each scrape and strike adds another tremor to the seismic record. The ocean itself becomes an amplifier, magnifying the glacier's mechanical unraveling. What once took centuries, slow movement, occasional cracking, is now happening in bursts of cascading violence. It's not just ice meeting water, it's a machine breaking itself apart from the inside out, loud enough to be heard across a continent.
The discovery beneath.
In 2021, scientists deployed a robotic submarine called Icefin beneath Thwaites Glacier. Suspended through a borehole drilled over 600 meters deep, the probe descended into the hidden world where the glacier meets the sea. What it found beneath the ice shocked even seasoned glaciologists. Instead of a smooth interface gradually melting from warm water, Icefin revealed something far more chaotic. The glacier's underside was riddled with vertical crevasses, deep jagged fractures that reached upward like frozen scars. Even more unsettling were staircase-shaped channels carved into the ice. These weren't random patterns, they were signs of targeted attack. Warm ocean water wasn't just eroding the glacier uniformly, it was exploiting weaknesses, flowing into fractures and accelerating basal melt in focused bursts. This discovery shattered long-held assumptions. Until that moment, most melt models assumed a fairly even rate of thinning beneath glaciers. But the Icefin data showed that melting beneath Thwaites is uneven, unpredictable, and far more aggressive than expected. The warm water carves upward into the ice, reaching zones once thought protected from erosion. Melt doesn't simply happen at the base. It now infiltrates from below, spreads sideways, and weakens the glacier from multiple dimensions at once. This chaotic melt geometry could help explain the increasingly frequent seismic events detected near the glacier's grounding line. The water isn't just thinning the ice, it's creating points of structural failure that align with where fractures later erupt. For scientists, this was a turning point. The glacier wasn't collapsing in the future, it was already showing signs of multi-front destabilization in real time. The ground beneath Thwaites wasn't just shaking because of surface collisions, it was trembling from within, as invisible forces worked their way upward through ice that had held steady for millennia, and was now coming undone. What happens if it fails? Thwaites is not just another glacier, it acts as a buttress, a natural dam, holding back the entire West Antarctic ice sheet. If it collapses, it doesn't fall alone, it pulls a continent with it. On its own, the melting of Thwaites could raise global sea levels by about 65 centimeters. That would be enough to intensify storm surges, flood low-lying cities, and redraw coastlines. But Thwaites is the trigger, not the total. Remove it, and the neighboring glaciers, previously stabilized by its bulk, begin to slide toward the sea. What begins as centimeters becomes meters. Entire megacities, from New York to Mumbai, face permanent inundation, and the threat is not theoretical. The configuration of the land beneath Thwaites makes it uniquely vulnerable. The glacier sits on a retrograde slope, meaning the deeper it retreats, the easier it is for warm water to rush in beneath it. Scientists call this marine ice sheet instability. Once it begins, the retreat becomes self-sustaining. Gravity does the rest. What's even more concerning is that many climate models, including those used by the IPCC, didn't fully account for the mechanical failure dynamics now visible at Thwaites. They didn't include the seismic data. They didn't anticipate under-ice staircases or rotating icebergs that slam with megaton force, which means those projections may be underestimating the true pace of change. Collapse might unfold over centuries, but the tipping point, the moment when reversal becomes impossible, could be years away. The future is not distant, it's already cracking into the present. The glacier is speaking. In the past, glaciers didn't speak. They moved with geologic patience, creeping over centuries in silence. But Thwaites has found a voice, and that voice is seismic. Every quake, every collision, every tremor beneath the ice is a broadcast from a system in collapse. Scientists are no longer just watching from space. They're listening from below. Expanded seismic networks now ring the Antarctic frontier. tuned not to tectonic plates, but to glacial stress. Each signal reveals fracture points, energy releases, and the growing instability of a glacier, once considered immovable. The data doesn't lie. Retrospective analysis shows a clear pattern. Seismic events have multiplied year after year. What was once monthly is now weekly. What was once background noise has become a real-time diagnostic. Thwaites is no longer drifting toward failure. It's actively disintegrating, and for the first time, humanity is learning how to hear a glacier break. The ice is no longer still. It fractures with force, speaks through tremors, and erodes from beneath. Thwaites is warning us, and the science is clear. Share this story, support Antarctic research, and demand climate action, because ignoring it won't stop the flood that's already begun.